Hello everyone, it's July 15th. Well, yesterday I said I'm gonna have to do it today in the evening again, but you know what? Decided against it and just let's get it over with right now. So the rest of the day, I don't have to keep this in my mind. Alright, let me get a piece of paper to get it started. Alright. I don't think it's something of concern. Nope. Alright, let's take a look what we have today. Valid triangle number. Ah, that sounds familiar. That sounds familiar, not because I've done it here. I think I might have done it in the Project Euler. That was a long time ago. Given an integer array nums, return the number of triplets chosen from the array that can make triangles. Oh no, I have not done this before. If we take them as sides, the triangle, the requirement is the sum of two lengths must be larger than the third length. That is triangle. Okay, valid combinations. 2, 3, 4. Using the first two. Using the second two. What do you mean using the first two and the second two? Oh, that's the only combinations. 2, 2, 3. I mean, no. Using the second two. Oh, using the first two. Wait, what? Using the first two. Oh, because these are different twos, so I'm using the first two, the second two. Okay, but it's a combination, right? Of 1,000. So the naive solution is just do a combination of 1,000. So C 1,000 choose 3. What's the result? So 1,000 choose 3. We're talking about 166 million options. Apparently, this is not going to work. Right? It's not going to work. Let's see. Which one is not valid? 2 to 3, 2 to 4. 2 to 4 is not valid because 2 plus 2 is 4, right? So basically we have a triplet and we need to make sure the smaller two, the sum of the smaller two is larger than the large one, because the other way around always works. Okay, so if we sort the number, right? Let's try to do this one. If we sort the number 2, 3, 4, and 4, right? So we sort it, and what we're saying is the smaller values, if we have any smaller values, then we try to add them together, and we just see if there's another value that is bigger than them, but it's smaller than the sum, right? So we can take, we say we want a 2, right? And then the second value we say is 3. Then we just need to see the sum 2 plus 3 is 5, right? So we just need to see how many numbers, how many values that are larger than 3. I mean, that's to the right of 3, but is smaller than 5. And we see 2, so we have 2 there. Now we do 2 and 4, right? 2 and 4, so that's 6. 2 and 4, so the 2 and then the 4, we have 6. And then we look to the right of 4. How many is smaller than 6? We have 1, so 2 plus 1. And 2 and 4 again, that's the second 4, which there's no more to the right, so we end there. Now we do 3 and 4. 3 and 4, that is 7, and then we have 1 more, so plus 1. Now 3 and 4 again, and there's nothing to the right. Now we have 4. Okay. So that seems to be a solution. So we sort it, O and log n to sort, and then we fix one value. Basically, we fix two values, right? We fix one value, and we go the second one. We have to go one by one, right? One by one until until the one before the end, and every time we find one, we calculate the sum, and we can use binary search for the remainder, right? Binary search for the remainder, and then see where we're gonna land, and we pick out all the values that's possible, and then we go to the next one, right? And we do the same thing. Go to the next one, do the same thing, and then we start. So that is going to be O(n) squared. With 1,000 length, O(n) squared is going to work, but it might not be the best solution, but it will work. Yeah, so yeah, it's going to be O(n) squared because O(n) squared is longer than O(n) log n. All right, so here's what we're going to do. I take a look at another, and this is also a hint, right? It's 0 to 1,000. 0 to 1,000. I'm thinking about the repeats. How are we gonna handle the how are we gonna handle the repeats? Hold on, let me think again. So, smaller values. If their sum is larger than me, then it's possible, right? 1,000. Let's just use this one first, and then so first one we're gonna say num.sort, right? Let's sort it. Then for I in range, I in range what? I have to say n equals len nums. So I in range, we're gonna from the first one up into actually this one, because we're gonna get a second one. Yeah, so this is gonna be n minus 2, n minus 2. And then for j in range, j is gonna be in range what? N minus 1, right? So we fix these two, and then we say bisect. So we're gonna from bisect, I'll just say import bisect. All right, so we're gonna say actually, yeah, I'm gonna say index equals bisect dot bisect. Let's go bisect. Go bisect left or go bisect right. So when we have the same value, right? So what if we have 2 plus 2 is 4, then we have 4. Do we want to go after 4 or before 4? We want to go something that's has to be big before. Yeah, it has to be before. So we're gonna go bisect left. Nums, right? And I plus j, right? So basically find where I plus j is going to be. And once we find that, everything to the, actually no, it's bisect right. It's everything to the, no, everything to the left. No, it has to be smaller, everything to the left. So we find the index, right? We find the index, and basically just from j to that index, whatever is in between is going to be our result. So I can just say in between, so these are smaller, right? So the index is this one and minus this index, right? So 4 minus 1 is 3. I think that's going to be minus 1. It's going to be res plus equal to index minus j minus 1. Yeah, I think it has to minus j minus 1. Because if it's the same, let's say, then the index will be this one, right? And then if I do index minus j, that's gonna be negative though. All right. I'm gonna write it out. So there's 5. 5 index is gonna be here. 0, 1, 2, 3, 4, right? 4 minus 1 is 3. That's 2, yeah. And what if I have 2, 2, and 4? So with 4, we say bisect left, which actually gonna go here, all right? And then when I say this minus this itself, what if it's 3? 3 is going to be pointing here. So that's the problem, right? If we have something that's the same, so we have to check, right? We have to check if it's the same, then I want, yeah. So let's say if bisect left, we're gonna go left, right? And we just say it's the same. We're gonna go left. What if the same is on the first one? That's gonna be 0. Yeah, that's the position we're gonna insert. Yeah, the return is a position we're gonna insert. So if it's a 0, then we have to say, wow, bisect left has, I feel like, a lot of edge cases. If the same, right? If a bunch of values are the same, is it gonna go? Oh no, we're gonna insert at this position. No, it's not like left. It's insert at this position, which is fine. Which is fine. So bisect left is gonna be that position. Yeah, it's fine. It's fine. I was thinking too much. So this minus plus, and then return res. And of course, I have to set res equal to 0. And be cheeky, we're gonna say something like this, right? Okay, so we have first test case 2, 2, 3, 4, 3. Second test case 4, 2, 3, 4, 4. All right, let's see. I mean, this one is possible for us to write a generic version, and we can have, like, if this one doesn't pass, we're gonna write the generic version. That is not what I had expected. Did I pass this thing wrong? What's index? Hold on. What's index? Index is 0. How is that possible? I think I might have, wait. And yeah, that's right. Nums and x, right? Nums and I. Oh, it's not I plus j. Yeah, it's nums I plus nums j. And I just realized we can push on the low, right? Low is going to be j plus 1. Num(x) is no such thing as num(x). Result 8. Oh, this looks very bad. Hold on, let's see. So let's just print. The num is already sorted, right? So we're just gonna print I, j, and index. So it's 3. Oh, j has to start from I. Actually, I plus 1. There we go. Alright. Okay, now second test case, both pass. Alright, take a look here. Edge case is a value by itself. Which is true. Alright, submit. Pending. Judging. Oh, we have a wrong answer. Oh, no, we accept it, but it's super slow. I don't like O. This is O(n) squared log n. I think it's going to be on the most right side. Not most right side, kind of on the right side. All right, so this is we fix two values. Fix two values, and use binary search to find where the possible third value is going to be. So this runs in O(n) squared log n, and we scored at 2,476 milliseconds, which is a 20% ranking. And apparently, we have a much better, something that's like twice as good, right? Twice as good. So let's give it another thought. Triangle number. How can we learn it fast? Are we like repeatedly computing some stuff, right? We like say 2, 3, 4, 4, right? If we compute to 3, we know how many there are. Can we know really fast if including 3 and 4 using the knowledge we have in the past? I mean, we should. I mean, 2, 3, right? Their sum is 5. So what we know is, say we know there are two values that's smaller than 5. And then 3, 4, they give us 7. And we already know that there are 5 smaller than 5. So for those, we definitely, right? So if the previous, okay, so what are we doing right now? What are we doing right now? We have the sums, right? We have the sums, and for each sum, we also have, so for each sum, let's think about this like a 2D array, right? So we have a sum. Let's say the sum is on the row, because the maximum is 2,000 rows, right? So we have a sum on the row, right? And we have, at this sum, where do we find it, right? Where do we find it? So we find it, let's say, at a certain position. So for 2, 3, 4, and 4, we say we have a sum of 5. I mean, actually, in this case, we probably should do a reverse instead of going the front, because reverse, we have better, yeah, let's do reverse. If we do reverse, let's say we find the first sum is 3 plus 4, right? 3 plus 4, the sum is 7, right? The sum is 7. So we say there are 1 values that's larger at position, so it's 0, 1, 2, 3, all right? So at position 2, so it's at 0, 1, 2, 3. At position 2, we have a 7, and we say we have 1 value that's to the right of position 2, and to the right of position 2, and it's smaller than 7, all right? That we can do immediately. And once that's done, we need to go, just 3 is first, and that's the second, right? And then that's it. So now we go 2, 2, 3, right? 2, 3. Actually, no, it's going to be, we start with 4, right? We start with the one before the last, and then we check 3. After we check 3, now we check 2. Now 2, 4 and 2, that's 6, right? That's 6. And we also have position 2. And can we say, we should go from the front, right? Because it's increasing. So the sum is increasing. So if we have certain number, yeah, because it's sorted, right? So everybody adding to me, I'm the largest. If I the smallest, we go smallest first, right? Smallest first. If we have a small, right? So 2 and 4 is 6, and we have 1 smaller than 6. 3 and 4 is 7. Then if we have 1 smaller than 6, then we're definitely going to have 1 smaller than 7. But we might have more if we want to go 7. But to see 7, we just need to know, in that case, what are we doing? What we're doing is we want to know at any position how many are smaller. So let's say we lay out all 1,000, or 1,000. Not really 1,000. I mean, just the maximum value and double the maximum value, right? So in this case, we're going to lay out 8. We start from 8, right? Start from 8. And the last position is going to be position 2. So if we say 8, right? How many is smaller than 8? We have 1 smaller than 8. And then for 7, how many is smaller than 7? If it's 1 smaller than 8, and we check this value, we check the max value is 4, right? So everybody is going to be 1 until 4. Right, 4 is going to be. Hold on, let me do this. So I have 0. No, there's no 0. There is 0. 0, 1, 2, 3, 4, 5, 6, 7, 8. All right, and then the column is going to be 0, 1, 2. We don't have to do 3. So 2 is the last position. So in the last position, because it's 4, all right? So everybody above 4 and included, that's going to be 0. Maybe it'll be easier to do it as a row. Yeah, let's reverse it. Position is going to be column. So it'll be 0, 1, 2, 3, 4, 5, 6, 7, 8. And the row is going to be 0, 1, 2. All right? So we're looking at position 2. If it's sorted, position 2 is 4. So we're asking at the position to the right of 4, how many numbers, how many values are smaller than 0, 1, 2, all the way to 8? So we know that it's going to be 0 for everything that's smaller than 4, and 1 for everybody larger. Okay, so that's that position. Now we're looking at position 1, right, which is 3. So if I look at position 1, that's 3, we want to look to the right and ask how many values are smaller than 0, 1, 2, 3, 4, right? So and then this is what we can do. We say how many is smaller than 0, and then we say the value the previous is 0, and the current value is 4, which is smaller, so that's still going to be 0, 0, 0, 0, 0. And when we hit 5, we say previous is 1, right, plus the current, right? Current is going to be, so it would be 2, 2, 2, 2. And then we call position 0 which is a 2. So we're going to see, so we added a 3, right? So it's going to be 0, 0, 0, 0, 1, 3, 3, 3, 3, right? So that's the table. When we have the table which take on times the maximum value, on times maximum value, we build this DP table, and then we look into the sorted array, right? Now we can ask the question. We say we do 2, 3, right? 2 plus 3 is 5. So we ask how many is smaller than 5 starting from 0, 1, 2, at 0, 1, 0, 1 to the right of position 1. So to the right of position 1 and 5, we find there are 2, right? And then 2 plus 4 is 6. So how many? So we're 6. How many to the right of position 0, 1, 2? We have 1 plus 1, and that's it. And now it goes 3 and 4. So 3 and 4 is 7, right? 3 and 4 is 7. So we want to see how many is 7 plus position is 2, and that's 1. And that's it, right? So this table, right? This table will take some effort to make. I'm not sure because we have to do the sort, right? After the sort, we need to do the table, which take on times the value. On times the value to make this table. Times the value to make this table. And eventually, when we do this, we have to go through exactly the same thing. It's just this will be O1 because we have the table already. So basically, it's just log n, on squared log n. This will be on squared plus on times the num, right? Basically, we're asking which one is faster. It depends. If we have long lengths, right, of a long length but small values, then I think this one will work. But if we have short length and large values, then I think this one will work. So maybe overall it's the same. Let's do this as our last attempt, and we will. I mean, can we like figure out the solution directly from this table? Directly from this table. I don't know. I mean, at this position, I don't know. Let's just do this one and then see how this one performs. So use a DP table to pre-calculate the sum of the key results, and then we don't have to use binary search when fixing two values. All right. So when I sort, when I do this, sort, do this, and DP is going to be, right? DP is going to be 0 times what? 0 times 0 times nums, right? 2 times nums minus 1, all right? Yeah, 2 times, this is column, then for this in range, n minus 1, right? That's a DP table. And then we're going to fix the DP table, which is going to be for I in range. I'm going to start from n minus 1. N minus 1. I think it's actually n minus 2. Minus 1, right? So for I in this, and for j, oh, it's actually not really for j. It's going to be, it is for j. For j in range, its starting value is nums I, right? Nums I actually is nums I plus 1. Nums I plus 1 all the way to the end. Where is the end? So the max sum is going to be 2 times nums minus 1. So this one is going to just be max sum, right? And this is going to be the max sum. Oh, we want max sum, so it has to be max sum plus 1. And this has to be max sum plus 1, right? So for j in this, dp ij plus equal to 1. Now hold on. So we're looking at this one, right? Shall look at not nums I. I think it's nums I plus 1. It's the next value. We're here, and we'll look at the next value, because that's the newly added value, right? The newly added value. And then we go from here to the end. So this is to create a DP. And when DP is done, this will be the same. And then this is just going to be DP. Do what? A J. That's not call. Let's call it. Oh my god. IJ used again. PQ for P is row or row and column. Row and column. RC. So for the DP table, right, the row is going to be C. Right? Row is C. That's where we are at. Right? And then the column is going to be nums R plus nums C. So nums R plus nums C. And we say that's how many is, I think that's the 1. Alright, let's try solution 2. Oh, first one we did not pass. Let's take a look. Let's take a look at the DP. Row in DP. Print row. Alright, this I already see problem with this one. That is not correct. No, so DPI plus, no, I'm gonna do this, range n, right? So I can say dpij equals, right, equals dpi minus 1 j plus 1. Let's see. That's still not the one I want. But we can analyze now. Alright, what is the problem? So for this one, it's the same DP table, and then we have 2, 2, 3, 4, right? So that's 3. I'm going to say 0, 1, 2, 3. I should start from here, right? Because, oh no, wait, that's 4. That's 4. 0, 1, 2, 3, 4. Everybody's 1. And then it's 3. This is 1. This is not 1. This is should be 2. Right? Because we're looking at this. We say we add a 3. And we say how many is larger than 0, 1, 2, 3, 4, 5 should be 2, but it shows as 1. Why? Nums I plus 1, num is 3, right? So 0, 1, 2, 3 plus 1 is 4, and then plus 1, and dpij, oh, I plus 1. Okay, well, we still have problem. This one looks more promising. Now we're looking for row. I shouldn't say row and column. It's just the first one. The first one is the second one. The first one going from here, right, and the second one going from here we go. That's the problem. Nah, I don't like this. I like to say it's the first and second. Like index 1, index 2, and this can be index 1, right? This is index 2, and index 1, and index 2. This one we pass. Alright, let's see if this one is any faster. I don't think so, honestly. I'm going to take a shot here. Alright, again, I should test the edge case. That should be 0 because we don't have enough value. Yep. Alright, try this one, see how fast. Nah, it's pretty slow. It might actually be slower. Yeah, it's actually slower. No, that's not the way. It's actually slower. But this solution is slower. Alright, let's see. 611. Let's see, what's the official one? Brute force. Oh my god. That's not gonna work. Binary search. Binary search. Yeah, that's the one. Square. That's this one. Exactly the same. Linear scan is ON solution. No, ON squared solution. All right, linear scan. Once we sort the array, we need to find the right limit of the index k for a pair of indices chosen to find the count of elements satisfying this plus this event for triplets. Form a value. Yeah, find this relevant by simply traversing the index k's value starting from index k for a pair ij chosen and stopping at the first value of k. Not satisfying. Again, the count for the elements satisfying. Okay. Supposing that when we choose a higher value of index j for a particular I, we need not start from index j plus 1. Instead, we can start off directly from the value of k. Save redundant computation. I think I know what it's talking about. Okay, that's way too fast. So this is good, right? And then this is not good. So with k we stay here, and we move j. Is good. Then we move not good. With k stay here. Move this. It's no good. And then everybody come back. And then this way is ON squared because j and k, they just, yeah. loop of kj will be executed. Reinitialize k. Nice. I think my solution is easier to read. And I cannot read. I cannot read the solution, man. I don't think because k only traverses once. Something wrong with the website. I cannot see a lot of the solutions. Sort plus 2 pointers. Ah, yeah, that's the same as the other one. All right, let's. Oh, I have more to write. And the number of numbers, brute force. The sort number for each. I need to find biggest k, such that it can be done binary search. Yeah, that's my solution. We need 2 pointers. So let's choose the first index. Then we need to find the number of pairs, left and right, where left is smaller than right, smaller than I, and a left plus an I. Let's start with left equals 1, and right equals I minus 1. Wait, is that? And then we can use 2 pointers approach to find the number of desired pairs for indexed I. Very similar to some. Let's see, what is I is going to be, okay, left and a right, okay, while left is smaller than right. If num left plus num right is larger than, we're going to count. Hold on, this is the key point. If num left and num right is, the sum is larger than, then count plus equal to right minus left, and then right minus equal to 1. How is this? What is this? Right minus left. These are pointers. And right minus left is everything in between. I don't understand. We choose first, and we need to find the number of pairs such that, and this plus this is larger than. We start with left and right. That should be 0. That should be 0. 2 pointers to find number of desired pairs. How? Count plus equal to right minus left. If left plus right is larger, then we move the left. If the left plus right is smaller, that means it's too small. Then we move the left. We move until it's good, right? If it's good, that means everybody inside this range will work. The left plus anybody inside this range will work. And after we work, then we decrease the right, and we try it again. Very, very good. I like this one better than the official solution. I mean, the official solution still works, right? So we have left and right, and we just traverse through the entire thing, and then we find the first one, and like we find one, and we store there, like we stop there, and we move. Oh, it's the same idea. It's the same idea. So this one fixed the right, the big one. The official solution fixed the small one. We fixed the small value, right? What we need is to find another pair where the small plus medium is larger than that. right? So we fix the left, so we still have a left and right, right? Left and right is just the same, and then we move right first, right? Because the sum is let's say the sum is larger than, right? Then we add everything in between, everything in. Now we can actually go to the rightmost, right? So the sum, if it's smaller than that, we move here, move until we hit it. And once we hit it, then we say, so like these two is larger than this, then everybody in between will work, right? So once that happens, we move the left, right? We move the left, so we increase this. Wait, do we move the left? No, we don't move the left, we move the right. We move the right. Are we always moving the right? Hold on, let me think about it again. So for each value, we go front and back, right? So if these two sum is smaller than the right, that means the right is too big. Then we have two choices, right? We can either move the left or move the right. We should move the left, right? Because it's too big, and we move the left because we need to keep the right as big as possible. Right? So we move the left until a point that it's these two sum is larger than this, so we can incorporate everything inside, right? Everything inside. Because if these two are larger than the largest, then they will be larger than everybody else. Okay? But then we are losing on this. I see like that, is this the only way that can work? These two sum is smaller. What if they're bigger? They're already bigger than this. If they're bigger, then we can move this. Yeah, I think it should be together. They should be together, right? If these two are bigger than this, then we move the right. We move the right into a position. We cannot move anymore. And then we say, now this is good, right? Now we're good. And once we're good, which means these two, no, if these two are bigger than this, then we're good, right? So we good until we fail, right? So we keep going until we fail. Now once we fail, then that means the sum is too small. Then we move the left. Yes, it's the same idea. It's the same idea as this. This one seems nicer, right? We find the large one and we say the two sums, right? The two sum, we're going to find two sums that's larger than me, right? So we start from the both ends and we say, if this is already larger than me, then everything contained inside will work. And we fix on the right and everything contained inside will work. And we shrink the big one and we'll try it again. If not, then we need to increase them. I mean, it's the same idea, the same idea. This one is just, it's not working very well. This is official solution on squared, but we are approaching this with the mindset of this Babichev mindset of Babichev. Okay, so same thing, we're going to do nums.sort. After we sort it, we're going to say n res equals len nums and 0, right? So for I in range to n minus 2, right? Now we have j, we have left and right. We're going to do left and right. So left, right. Now let's call low and high. Low and high equals I plus 1 and I plus 2, right? We say while nums I plus nums low is larger than nums high, right? If this one happens, then rest plus equal to 1 and high plus equal to 1 until it fails. Now once it fails, then we move the low, right? We move the low. And we say while nums I plus nums low is, no, we just keep moving high, and it's not good we're moving, yeah, and not good we just say low plus equal 1. And this one will happen inside another loop called while low is smaller than high. Right, low must be smaller than high, and then it goes through this. If it's bigger, if it's initially it's not big, then we just exit, right? If the two is the sum is larger than the third one, then we move the third one, right? Because the current is good, so we want the high to be more challenging. So we move the high, and then it's still good until we cannot. That means it's too challenging, so we move the low, right? We move the low, and then we go through that again. And eventually this will end when we keep moving low and the low and high meet each other, right? And then we go on to the next iteration. So we're going to turn rest. Try it. Solution 3. We have index out of range. So high can keep adding. If these two is larger and larger, and well, we do need to have so while high is smaller than n minus 1, it's smaller than n, and this. Okay, we fail on this one. Why is that? Why is that? So we have 2, 3, 4, 4. 2, 3, 4, 4, right? So I is going to be 0. So this is I. This is low. This is high. And while low smaller than high, if high smaller than n, yes. And nums I plus nums low is larger than nums high. Then rest, okay, with plus 1. And high, move on to the next one. And then we do this again. So plus 1 again. And high, move on to the next one. Now we exit. Alright? And then low plus equal to 1. Come back. High is already exit. So actually, we can put it here as well. While low smaller than high and high is smaller than n. Right? Do this check. Then the high will immediately exit. So we got 2. So now I is going to be here. I is here. So low high is here. And we do 1. Yeah, it is 3. What's the other one? To give it 4, 2, 2, 3, 4, 2, 3, 4, 2, 4, 4. That's the other one. So 2, 3, 4, 2, 3, 2, 3, 4, 2, 3, 4, 2, 3, 4, right? But we don't do 2, 4, 4. Why we don't do 2, 4, 4? Because the low never plus. Let me see. Low plus equal to 1. These two is good, right? So I keep moving this. But why I need to move the low as well. But I say we move low whenever we cannot do it anymore. But shall move it. Hold on. Say the sum is larger than this. So it's not challenging enough, right? So we need to move, and then move to the end. That's done. Once we're done, shouldn't we do low plus equal to 1 no matter what? We do low plus equal to 1. So low move here, and then if low moves here, then we reset high, and we repeat the same thing. I don't know. Why this one's not working? Just low, I can keep going, right? That's the problem. Low, I can keep going. Like when this one is finished, and this one is finished, at low plus equal to 1, and that become the O(n) triple solution. It's not O(n) squared because we scan through the entire thing. And in the official solution is we scan until we cannot scan anymore, right? And then we stop. We stuck there, and then we move. Yeah, we scan until we cannot scan anymore. Then we move. This one, and we keep scanning, which means we probably should stop. Good, and then we do this, and how would this one work with this? Hold on, let's check the solution. All right, so I is this, k is I plus 2. For j is from here to this, and num's I is not equal to 0. Num's I is not equal to 0, and j plus plus. K is smaller than this, and this plus this, and k plus plus. Count equal. I think this is the key. This is the key. We shouldn't do this. We keep going, keep going, keep going. Ah, yes, that's the key. So, no, it's not here. So we have low and high, right? And then if I and low is larger than high, that means not enough high. We go keep going, keep going, keep going until we cannot go anymore. That means everything in between is fair game, right? If like this plus this is larger than everything, then this plus everything in between will also work, which means we have every pair inside is a good pair, right? which means now high is here and low is here. So everything in between is fair game. Hold on, let me think again. What does this mean everything between is fair game? Which means I can, because we're talking about these sum of these two, right? And then we say we can go all the way. So these sum of these two is larger than any of these values, right? And that means sum of these will also be larger than any of these values. Sum of these will also be larger than any of these values, which means sum of, so we can do this, all of this, plus this, and all of this. I still don't understand. And read again. Yeah, k plus plus, and then for j, so we stuck j's here, so ij is here, and then this is high, right? And then we go through the entire thing, and then we say, basically we're saying everybody inside is fair game, right? Because this is plus, and then we keep going, keep going, keep going, and then once we stop, everybody inside is good to go, right? That's good, that's good. And then, now because I am currently, the high is currently residing in the high place, let's say, so I'm going to move j now. So we're going to move j here, and we're going to check again. So we move j here, and then we need to check again. That's the problem. So the low needs to always move. The j needs to always move. So we're going to say for j in range I plus 1 to n minus 1, right? And then k, yeah, let's just say k, right? K is equal to j plus 1, right? And we say while k is smaller than n, yeah, it's official solution. While k is smaller than n, and nums I plus nums low is larger than nums k, then we increment k, right, until we cannot do that anymore. And once we cannot do that anymore, rest plus equal to k minus j plus 1. No, k minus j, k minus j minus 1, right? So that's the result. And then keep going. Low is not defined. Where? This is j. Now the pass. Let's try it. Oh, have a error. Yep, that is an error. Oh, that's a time limit. Wait, what are you talking about? Oh, because we set k here. No, k should not be set here because k do not reset. We keep k as it is, so k shall be here. K shall be I plus 2. And then j and then k keep moving, and then we don't move k anymore, right? and then with j keep moving, and then we compare if it's good, if the sum um, is big, then we can keep moving until we cannot move anymore. Yeah, k should be here. Now a wrong answer. Output -1. What the hell? So I saw the trick that they're doing. I want to know why. Okay, so 0, 1, 0, 1, 0, 1. This shall give us expected is 0, but I'm giving -1. That's actually 2. That's not j, it's I. Alright, let's take a look at the last one. So what we have is 0, 0, 1, 1, right? And starting I is here, j is here, and k is here, and we say num is larger than no, so res equals k minus j minus 1, that's 0, right? And then j move on. Now when j move on, k and j, they're together, right? And we still don't do it. That's a -1. That's where -1 comes from. So I think it has to be j has to smaller than k. Oh, hold on. K, j, and then here. I think if j is smaller than k, then we do this. Yeah, j has to be smaller than k. If j is not smaller than k, then we just j go to the other side, right? And if j is smaller than k, we do this and continue. If j is not smaller than k, right, that means j already entered the k territory. So else, I think else we can break. We don't have to keep going because k is not moving, right? K is not moving, so it's too small. All right, so we add this. Have to run it again. Yep. All right, try it again. Pending, judging. There we go. It's a little bit faster. It's a little bit faster. 3 sums smaller, I see. What are these solutions then? Ah, this is the other one. Ah, this is the one that guy provides. We have a value on the right side, right? And then a small index and medium index. Well, if this is larger than, if they're larger than me, that means they are good. So we can decreasing the medium index, right? Decreasing the medium. I like how it's called medium index. We can count everything, and then otherwise we can increase the small index. Let's do this. Solution 4. In this sense, this one is a more natural, I think. More natural way. So like nums and 0, right? So I should credit. Hold on, I think it's this guy. The 2 sum three-sum solution. Reference. Right? Two-sum, three-sum solution. So we sort these, and then we say for I in range n minus 1, to 1, right? So we can only get to 2, and then I'll just call it mid, right? And then low, no, this is high. High, and then low, mid equals low is 0, mid is high minus 1, right? And we say while low is smaller than mid, if nums low plus nums mid is larger than nums high, so we're good. If we're good, then everything in between is good, right? Because the low and the mid is good, because low is the smallest. So everything in between plus the mid will be larger than high. So we say res plus equal to mid minus low. Do we need to minus 1? 0, 1, 2, mid minus low. Yeah, I don't have to. So just mid minus low, and then we finish using mid. So we need to make it more challenging. So mid minus equal 1, right? Else, if they're smaller equal to, which means it's too small. So we need to up the game. So low plus equal to 1. And then return res. So solution 4. I'll pass. I like solution 4. I like the official solution for two-sum, three-sum. I hope I can remember this when in the future, I think I'll do the two-sum, three-sum problem. I did three-sum or two sums already. It's not the three-sum. Wow, this is faster. Very good. That's very good. I like this one. All right, that's it. That's it for today. See you guys tomorrow. Adios.